This is week 6, and today we're going to talk about something called stoichiometry, which is just a big fancy word telling you how things react together in a chemical reaction. I actually love this quote from John Wesley: "When you set yourself on fire, people love to come and see you burn." I think that's a wonderful way to live your life in the spirit. Now, a chemical equation is simply a symbolic representation of the chemical reaction which is occurring in front of you. At the top here, we have the symbols that show the chemical reaction for the burning of methane. Methane is CH4. It combines with oxygen to form carbon dioxide and water. And you'll notice they put the word coefficient above the two places where a 2 is put in front of the symbol for the molecule oxygen and the molecule water. And the coefficient just means that it takes 2 oxygen molecules to combine with 1 methane molecule, and it produces 1 carbon dioxide molecule and 2 water molecules. And this is shown in the middle, how this happens. And you see you have 2 sides to the equation. There's the reactant side, which is the substances that are undergoing the reaction and are on the left side of the main arrow. And then there's the product side, which is the substances that are produced by the reaction, and they're on the right side of the arrow. The coefficients are the numbers that represent the relative number of each reactant undergoing the reaction and the relative numbers of the products that are produced. So if you were going to write that equation in English, you would say that 1 molecule of methane combines with 2 molecules of oxygen to produce 1 molecule of carbon dioxide and 2 molecules of water. Now this picture shows you the reactants before that are mixed together and the products after that are present. Now what this tries to show you is that when you take into account all the atoms on the left side and all the atoms on the right side, you have to end up with the same number of each atom on the left side and the right side. In order to do that with our equation, we have to do what's called balancing. An equation where there are an equal number of atoms of each element on both sides of the equation are called balanced. If you were to select out, let's say, the red circles, which I'm not telling you what those are yet, but you'll notice that there are 6 doublets. So that means a total of 12 red blobs. If you were to count the number of red blobs on the right side, you would see that there are 12 red blobs on the right side as well. So let's take a look at how we would go about balancing equations. And in this case, we're just looking at them and see how they are balanced. So the first one is a combination of phosphorus and oxygen to produce phosphorus oxide. In this case, it would be tetraphosphorus decoxide. And so you start out, P plus O2 gives P4O10. Now if you look here, you have 2 oxygen atoms here, you have 10 here, so if you put a 5 coefficient in front of that, you'd have 10 oxygen atoms here and 10 oxygen atoms here. You have 4 here. And if you put a 4 coefficient in front of this, you would see you have 4 phosphorus atoms and 4 phosphorus atoms. And so this is now balanced, a balanced equation. 4 phosphorus atoms combined with 5 oxygen atoms to produce 1 tetraphosphorus pentoxide. Let's look at the next one. BaCl2, or barium chloride, plus sulfuric acid combines together to produce barium sulfate plus hydrochloric acid. Now when you look at this, you see you've got 2 chlorines here, but you've only got 1 here, and you've got 2 hydrogens here, and you've only got 1 here. But if you put a 2 in front of this, now you have 2 hydrogens, 2 chlorines on this side, 2 hydrogens, 2 chlorines on this side. Let's look at the rest. You have 1 sulfur and 4 oxygens here, 1 sulfur and 4 oxygens here. You have 1 barium here and 1 barium here. So now this equation is now balanced. Let's look at the third one. This is hydrogen plus nitrogen combines together to form ammonia. Now you have 2 nitrogens here, and you only have 1 here, so let's put a 2 here tentatively. Sometimes when you do these, you should use a pencil, because you may have to erase. You have 2 times 3 is 6 hydrogens here. You only have 2 here. 2 goes into 6 3 times. So if you put a 3 in front of that, now you have 3 hydrogen molecules plus 1 nitrogen molecules forms 2 ammonia molecules. 2 of these and 2 of these, 6 of these and 6 of these. So you now are balanced. Stop the video at this point and try this last one on your own, and then I'll do it and we'll see how you do. Okay, so we have C2H6, which one day you'll learn is ethane, combines with oxygen to form carbon dioxide plus water. By the way, this is a combustion reaction. Anytime you take something like this and combine it with oxygen, it's combustion. This is just burning ethane and oxygen. Okay, so you start out, you have 2 of these. So let's put 2 in front of this. You have 6 of these and 2 of hydrogens on this side, so you need a 3 here. So you have a total of 2 times 2 is 4, plus 3 is 7 oxygens. Now, a 7 means you'd have to have a 3.5 here. Well, we don't have halves as coefficients, so you multiply the whole thing by 2. 2 methane, plus 7 oxygens go to form 4 carbon dioxides plus 6 waters. You have 12 hydrogens on this side, you have 12 on this side, you have 4 carbons on this side, you have 4 here, you have 8 plus 6 is 14 oxygens here, and 7 times 2 is 14. Moving along, let's talk about different classifications of reactions. One type of reaction is called a precipitation reaction, and you can see this on the left here. You have a layer of solid on the bottom, that's called a precipitate, and then above that is what's known as the supernatant. And a precipitation reaction occurs when one of the products is insoluble in the other and it drops out of solution. The solubility of any substance is equal to the maximum concentration of that substance that can be achieved in any particular set of circumstances. When something is soluble, it means that a large amount of the material will dissolve, a large amount of the solute will dissolve in the solvent. A precipitate occurs only when the solubility is exceeded, and as shown in this case. Something is insoluble or called insoluble when it has a low solubility. Here is an example of another type of reaction. This is called an acid-base reaction, and this occurs when a hydrogen ion, represented by H+, is transferred from one molecule to another molecule, and this is what you see in A and in B. Primarily in A, I'm sorry to say. I'm sorry, A just shows the two are set up together, starting as a gas and becoming a liquid. But B shows the acid-base reaction. And what you see here is the combination of aqueous hydrochloric acid with water, and the hydrogen ion is transferred from the hydrochloric acid to the water molecule and forms what's called a hydronium ion, H3O+, plus chloride ion. The acid is the substance that dissolves and releases a hydrogen. So it's what's called a proton donor. And the base is the substance that releases the hydroxide, but it's also the substance that accepts the proton. So it's a proton acceptor. Now, a salt is the substance that's formed when there's a reaction between an acid and a base in the process of neutralization. A strong acid is an acid where the molecule completely releases all of its hydrogen ions and forms a large number of hydronium ions in reactions with water. And so it's when it's complete or almost complete. Obviously, a weak acid would be one that does not completely release all of its ions. And that's what's said right here. Acids that do not completely release the ions and form hydronium ions in water are called weak acids. Strong bases, on the other hand, release or completely release OH ions, and they also are very avid acceptors of hydrogen ions. And weak bases do not completely release OH ions in water. Stoichiometry, this really fancy word that scares a lot of people, is actually the process to relate the balanced equation. So you start out with the balanced equation that we've talked about already, and we relate that to the real-world calculation in chemistry. It's like a recipe in cooking. What is required and what is produced. So for example, in this reaction, you have 2 molecules of aluminum combining with 3 molecules of iodide to form 2 molecules of aluminum iodide. This tells you need 2 parts aluminum, 3 parts iodine to form 2 parts aluminum iodide. So when you do that in the real world, you know you need 2 of something of aluminum, 2 molecules, 2 atoms, if you want to call it. And so this thing acts as a recipe to show you how to put this together. And so what we can measure, if you remember from last week's lecture, we can measure moles. And remember that a mole represents a specific amount of the substance, but it also represents a specific number of molecules. So if you have a certain number of moles, you have a certain number of molecules, and the relationship between moles and molecules becomes important because you can now restate this equation here as 2 moles of aluminum plus 3 moles of iodide forms 2 moles of aluminum iodide. So now you've gone from molecules to moles because there's a direct relationship between those two. And you can answer the question that's been given here. How many moles of iodine are required to react with 0.429 moles of aluminum? The moles of iodine are related to the moles of aluminum by what's known as the stoichiometric factor. And the stoichiometric factor is the ratio between those 2 coefficients, 3 and 2. So for every mole of aluminum, you need 1.5 moles of iodine. Conversely, for every mole of iodine, you need 2/3 of a mole of aluminum. So the stoichiometric factor here is 3 iodine over 2 aluminum. And so all you have to do is take the number of moles of aluminum and multiply it by 3 over 2, and it tells you you need 0.644 moles of iodine. Now, if we want to do the transposition between, the first one there was moles to moles, this one is moles to molecules. How many carbon dioxide molecules are produced when 0.75 moles of propane is combusted according to this equation? So let's take a look at this very carefully. You see you have one molecule of propane reacts with 5 molecules of oxygen to form 3 molecules of carbon dioxide and 4 molecules of water. So the moles of propane you use the stoichiometric factor, which in this case is 3 over 1, to find the moles of carbon dioxide. Once you know the number of moles of carbon dioxide, you just multiply that by Avogadro's number, and you know the number of molecules of carbon dioxide. So you would take 0.75 times 3, then times Avogadro's number. And that's what we're doing right here. This is first the stoichiometric factor, which is 3 over 1, 3 carbon dioxides for 1 propane, which comes from your balanced equation. Then you take 0.75 times 3, that tells you the moles of carbon dioxide. Then you multiply, which is 2.25, then you multiply that by Avogadro's number, and it tells you that you have 1.4 times 10 to the 24th molecules of carbon dioxide.